Good morning, everyone. Welcome to ENGR 1330 sections 003 and 004, fall of 2020. And so you just completed the first exam, which is still being graded. And on first glances, I don't think anybody needs to worry about repeating this class unless you really want to. But we'll get back to you when it's completed and ready for return. So today's topic has a strange title, I would presume, called Causality and Simulation. But we're making a fairly big intellectual change from what we've been doing so far. So initially we were giving you tools, Python being the one that we were required by our design team to present you, and giving you bits and pieces. And you've learned Google, and you've learned how to Google Python, how do I do something. Now we're going to start putting those pieces together in support of some various data science applications. I guess in the modern vernacular, that's called scaffolding. So we have little functions that we can get to work ourselves, all of us. Some probably more skillfully than others. That's the way it is. But we want to scaffold them together in a structure to accomplish a particular task. So I'm just starting off that before I do anything on the screen or even turn on the screen, to sort of get your mind in gear that we're making a fundamental mental jump here. Not to something harder, but to something different yet related. And so you keep in mind as we're doing examples from here on that these are scaffolding pieces from earlier works that we've done. So now I'll go ahead and share my screen. And we'll do the full screen share. Am I going to regret that? Yeah, probably, but that's the way it is. I think I can close that without losing the connection. Here goes nothing. Good. And let me get to our Blackboard homepage. Actually, I'm in the lesson collection. So today we're on Lesson 10, Causality and Simulations. And if we descend into the directory, there's the usual web link, which we will take shortly. There's a folder with the laboratory contents that itself is just a web link. And is the back button going to work? And then there's the actual Lab 10 assignment where you will upload the results of your Lab 10 exercises. So I will take the web link, and just by way of warning, the network nationally, this is not just a Lubbock thing or a My House thing, has been working poorly the last 4 or 5 days. So if at some point this thing halts, it's not your fault. It's who do we want to blame this week? AT&T, T-Mobile, the government, the Russians, the North Koreans. You pick one. Currently, it's not working as well as it did a few weeks ago. And case in point, right here. It's just sitting there, waiting and waiting. Now, I would imagine with 100 web requests all going to this particular URL, there might be some slowness caused at the West Virginia gateway where this stuff is hosted. And boy, that's taking a long time. Now, I've got it up here in the tab, but it's not much of a test if I can't actually link to it. I'll do this the hard way. Let's see what's going on. Maybe it'll come to life. We're in burst mode, so we're good there. Four minutes of CPU time. This thing should be running. Wonder if it's my computer. So we will attempt to, yeah, it looks like I got an Apple surprise working right now. So I will blame Apple for all my woes today. That's exactly what it was.
It does not load on my side either.
It's not loading here either. All right, there's a solution. It's going to take me about 2 minutes to implement it. God, I hate to give away almost 100 minutes of clock cycle, but I'm going to have to. Let me see first if I can actually connect using the Amazon management software. Okay, that's not good. There's oh, I bet I know what's wrong. Let me check something. 3 megs. It is in the midst of a file upload. Looks like I still have access to it. Nope. Okie doke. All right, we'll just shut it down, restart it. There's a day's worth of CPU clock cycles just flushed down the toilet. And we'll wait a minute or two while it's resetting, which gives us a good time to have a short conversation with everybody. And the topic of the short conversation is we should always have local capabilities to do our work. So yeah, I've been using Amazon Web Services to store all of the content for this class because, with the exception of right now, it's usually superior to using university-supplied resources. We introduced you all to CoCalc as an attempt to avoid having to walk 100 people through Anaconda installs, because it just takes one failure to make that a nightmare process trying to do it all remotely. But over the course of the next few weeks, based on our midterm exam experience, I think it would be a good idea to consider getting Anaconda installed on one of your personal machines. And it's not hard to do. Farang and I were talking about possibly hosting a workshop over the over this weekend coming up and going through an Anaconda install on a Windows 10 environment, and then I'll do it on this particular Macintosh that you're watching right now. Braden, the internet has been bad since forever. So the reason you don't understand is you've not been badly impacted. But if your internet service provider is AT&T or Suddenlink, who operates under the we don't care, we don't have to method of customer service, the internet fails from time to time. Also, the other explanation, Braden, all of us that are physically here in Lubbock, Texas, all of our communications goes through a gateway, and I think it's physically located in Amarillo. If you were to run the trace route program on 2 different machines at 2 different locations in Lubbock, even one on campus, there would be a common dotted quad IP somewhere in that route that usually represents the regional gateway. So all the traffic is going through one physical point. If that thing is clobbered or congested with traffic, then you have a problem. The Amazon Web Services, I'm actually stalling now to give it a chance to completely clear its stack. The Amazon Web Services, I'm using a West Virginia location. There we go. And we're trying to restart. The Amazon Web Services, I'm using Virginia Zone A. It's located on server rack 27 on the 4th floor of some nondescript building in Reston, Virginia. So physically, everything still has to go to a single point. And the current internet is clobbered with a bunch of YouTube videos of cats jumping around, which are fun to watch, but it uses up everybody's bandwidth. Okay, so I should have control again. Let's first terminate those 2. Leave the page. Terminate that. Terminate it again. Okay, let's find out if that's a legitimate connection or just lucky. Sweet. Okay, so seem to have regained control of the remote machine, and let's see what that cost me. That's not too bad. It looks like I was able to retain all of my prepaid minutes. Okay, so now let's get back to our class and quit listening to me babble aimlessly. So today is Lesson 10. There's 3 links in the index page. Lesson 10 is Jupyter Lab, which is the one we'll take in a second. The original PowerPoint, which has the materials that are specified by the 1330 curriculum team, and we will look through that. And, oh, classic. Actually, it doesn't work. Open with what? Well, there's the PowerPoint right there. And then there's the laboratory, which you will find a single notebook in. Let's see what those... So I'm going to open up the actual PowerPoint. And we'll get started, and then I'll actually switch to my notebook, which has the same content. Currently, you see the black screen of nothingness. And so causality and simulation. So the topics are causality and simulation. Iteration is an ancillary topic that you've already had exposed to when we were talking about loops, count-controlled, sentinel-controlled repetition, and this is just an application of that. And the overall objectives are to understand what causality is, concepts in iteration and simulation. And all three of these topical areas are an important part of algorithm design, and simulation is the main umbrella topic of computational model creation. And now we will leave these slides and we'll go to my versions of them. So I'm going to try to leave this running in the background in case I need to refer to it. So you're getting extra bonus feature today. You're getting 2 presentations, which will make it doubly difficult to understand what's going on. Okay, so there's that one. And now I need to get to the correct... Go away! Oh, that's frustrating. There we go. That's where I wanted to be. And I want to take, I think development is the best one. All right, so this is stuff that you all can see if you wish. It's on the content server at the link. I'm trying to make a little bit more room. There we go. So I've entitled this the first of many lessons in data modeling. And there's several different approaches to data modeling that we're going to visit. And this is the first of them, which I've called the statistical approach. The objectives of this lesson are to understand fundamental concepts in causality, and more importantly, the difference between cause and correlation. Because despite what our textbook says and other books, it's difficult, if not impossible, to establish cause simply by data science approaches. But correlations are quite straightforward, and they're useful. We also want to refresh our fundamental concepts in iteration and understand concepts in simulation. The computational thinking aspects of these are listed here. Causality, iteration, simulation are used in algorithm design, and iteration and simulation themselves are a major component of creating computational models. The textbook that we have, the Data 8 textbook, most of what we're talking about today is taken from this chapter called Randomness, and in their textbook they present some various scripts that leverage certain parts of the Python language and the supporting subsystems in NumPy and Pandas to help us construct models of probabilistic behavior. And I will leave this to you to read on your own. In this book, there is something called the Monty Hall problem, which we are going to replicate. In fact, you will notice that the graphics in my notebooks look amazingly like this one. It's almost as if I screen captured it and then embedded it. So we'll see that again. But this section on randomness, you should read it because it is your textbook. And oh, that's right. It spawned a new window. Did it? Yeah, it spawned a new window. So let's talk about correlation and causality, and then we'll actually get on to making the computer do cool stuff. So causality, first a long-winded explanation. And I'm literally going to read this to you. Causality is the relationship between cause and effect. The notion of causality does not have a uniform definition in the sciences, hence it appears in every statistics book ever written, and is studied using philosophy and statistics. From the perspective of physics, it's generally believed causality cannot occur between an effect and an event that is not in the back or the past light time cone of the effect. Similarly, an effect, a cause cannot influence something outside its future time cone. They're using light cone in this sentence, but they mean time. And then there's some recent articles on closed time loops. I mean, so if you're like a Doctor Who fan, these are both physics articles, and I'm going to look at the second one because I want to make an important point about this. So here's the article. This is written by one of these two authors. I think Fabio is an undergraduate student just like you. Obviously a bit of a genius, unlike the rest of us. And he wrote this article, and it appears in Classical and Quantum Gravity. And he's talking about time loops. And this has been recently attributed as the first article that explains causality and theoretically allows for time travel without those pesky paradoxes of if you go back in time and you punch yourself in the nose, does that change how many butterflies came out of the dinosaur's belch? So this is good fun reading if you have nothing better to do. And then there's another one in American Physical Society Physical Review Letters along the same context. And what's important about both of these, they explain something called causal consistency. And causation is a really big deal in classical and relativistic physics. So in classical physics, which we as engineers pretty much embrace without question, an effect cannot occur before its cause. So let's think of an irreversible exothermic reaction involving nitrocellulose, or what most of you all would know as a bomb. So nitrocellulose is a relatively easy chemical to fabricate. You can make a close approximation using potassium nitrate, which can be harvested from feces, and a few other common compounds. And sugar's a good part of the propellant. And you have this physical mixture of relatively common chemicals. Most of you, with what you have in your own house, could make an effective yet poor yielding exothermic chemical reaction. And as far as we know, that reaction's one way. So that stuff will sit there all nice and inert in a small container that you've done just for this mind exercise, because if you did it in real life, I think you'd be breaking all sorts of laws. And then if we apply a source of ignition, so that's our cause, we apply a very concentrated source of heat. Actually, these are percussion sensitive. If you give it the right physical impact, that chemical reaction will begin. It'll give off a whole lot of energy. It'll go boom, there'll be a flash. And if nobody gets hurt, it'll be a lot of fun. Everyone will laugh. Those things don't go off spontaneously. That source of ignition has to happen. That source of ignition caused the explosion. That's classical physics. So we can't have an explosion without the source of ignition. In special relativity, it takes those ideas a little further, and it deals with the relative temporal relationship of the cause and the effect. And then as we're moving on, and I go yada yada blah blah, so there's a whole bunch of theory on what causation is. I think I'm going to go to a simpler approach, which is the cause and effect are whatever answers a why because literary structure. So why are there more lawyers in the United States? Because more money is spent on pets. So that would certainly be a why because structure. That's absolutely absurd. What I've just articulated in words is correlation. But for causation, think of cause inducing an effect. And that's probably sufficient for the time being. If you get interested in it, you've got some readings up there that you can pursue on your own. But let's look at a related term, which I call causality's mimic, correlation. Correlation is useful, and we can find correlations in data. And then whether those correlations are meaningful in an engineering sense is very context sensitive. So let's look at this chart again. So here we have in orange the money spent on pets in the United States. So over time, as people acquire more and more, as pet food gets more and more expensive, amazingly, the number of lawyers increases. So clearly, these two lines, they look almost right on top of each other. They're not, but they're almost. And so one statement we can make is the correlation between money spent on pets and the number of lawyers is quite good. I would argue it's nearly perfect. There's a slight bias, but the correlation is almost one-to-one. So it begs the question, does having pets cause lawyers? Well, of course not. Does having lawyers cause pets? That's quite possibly true, because one thing lawyers get to do is they get to put in jail all of their mistakes. And so if you argue that jail is not much different than a dog crate, except that you're putting people instead of dogs in the crate, then maybe lawyers do cause pets. Of course not. Either of those assertions is absolutely absurd. What's more likely happening is that the general socio-economic conditions that improve overall wealth for a society create sufficient disposable income that people can afford to have pets and choose to do so. Well, those same social economic conditions that improve general wealth also improve the number of charlatans and cheaters. Hence, you have to have more lawyers to hunt them down and kill them. And so that's what this chart is showing. So what I've just explained is correlation. There's a nice YouTube video that about correlation and causation. I'm pretty sure that this one is I think this is a Khan Academy video. I don't want to take the link and clobber my network. Again, that's for you to watch on your own time. It is indeed part of the lesson, so we may test on it in the future. Let's look at another document. So I have a document called TWRI 4 Water Resource Techniques of Water Resources Investigation, Book 4, Chapter A3. And in that book, there's these sentences that are they start in a chapter of that particular book, and it reads as follows: concentrations of atrazine and nitrate in shallow groundwaters are measured over wells over a several county area. For each sample, the concentration of one is plotted versus concentration of the other, and it's observed as atrazine concentrations increase, so do nitrate. So the question that can be begged, does atrazine cause nitrate? More likely, they're associated with one another, and a question we would have is, how do we measure the strength of this association? Similarly, imagine streams in the Sierra Nevada mountains in California usually receive less precipitation in November than other months. Has the amount of November precipitation increased over the last 70 years, showing a gradual change in the climate of the area? How might this be tested? This is actually a really good sentence because it introduces a concept called confounding. So as we're introduced to the concept, we're talking about streams draining, less precipitation in November, and then the question is, has November changed significantly? Presumably, the answer would be in part, what is the stream flow over the last 70 years versus the recorded precipitation over the last 70 years? Are they trending in the same way? If the answer is yes, then perhaps there is a relationship. So both those situations require a measure of how well associated the two variables are. And one class of measures that's used to do that are called correlation coefficients. And we're not going to study correlation coefficients specifically today, but it's coming up on the guitar pretty soon. So causality in the context of this course is almost always a surrogate for correlation. And in the lines of that correlation, it's not only enough that we can observe a correlation, we also want to know if that correlation is explainable simply by chance or if the correlation is telling us more. And that would be our first steps towards trying to establish causality. So moving on, the implications of all this babble are that most research questions that we employ in engineering research are some versions of an attempt to explain cause and effect. So in experimental research, when we go to the laboratory and build widgets and hook up machines that go ping and then directly connect them to a sponsor's credit card, those experimental relationships are usually constructed in advance, and we would consider the experiment itself somewhat of a failure if none of the presumed causal variables actually influence the response. So if eating broccoli does not improve the survivability of COVID-19 patients, then clearly broccoli is poisonous and shouldn't be eaten. That's probably a really piss poor and untimely example, but usually when we build a physical experiment of some kind, we have some idea of what the causes are. In fact, we're supposed to if we're using a scientific method, because cook and look experimentation is discouraged. And if none of the causal variables influence experimental outcome, then that experiment would be declared a failure. Not a failure in the sense that it wasn't worth doing, but a failure in the sense that none of our causes had any effect. In a data science experiment context, it's a little harder to do. So causality itself may actually be impossible to establish. However, correlations can be established and exploited. There's a big company that's currently hosting this website for me called Amazon that built its financial success on correlation because they figured out how to exploit those correlations. They found out if 1,000 people bought a certain type of product, it was likely that another 10,000 people would if we could just convince them to click on the Buy Now button. And they put a lot of psychological research into making that happen. In data science, however, studies involve observations on groups of individuals, and one of the factors of interest is called a treatment. This is coming straight from the Data 8 book, or an explanatory variable, or a predictor variable, or a predictor feature. It's got a whole bunch of different names. These are the presumed causal variables. And then there's an outcome, sometimes called a response, an effect, a predicted value, a system state, and several other names that are measured in each individual. And so we would apply those segregations of by individual, by treatment factor to different statistical tests in hopes that we can establish some causality and hence exploit the predictor variable to our advantage. So the presumptive establishment of causality takes two stages. First, we observe an association. So any relationship between treatment and outcome is called an association. We can measure the strength of the association using correlation coefficients. Once we've identified the association, we then want to attempt to establish causality or cause-effect. One approach would be to control all the variables other than the suspected explanatory variables. And I stipulate that for any meaningful process in data science, it's probably impossible, because that's getting back to the experimental research construct. Another approach is to establish randomized control studies. And if you've been watching the news over the last 6 months, there's been vigorous arguments on whether this is necessary for coming up with therapeutic and vaccination drugs for the COVID-19 virus. And both sides of that argument stand to gain a lot of financial advantages by them being right, and I forgot where I was going there, so I'll just continue. So a randomized control study follows some process like listed here. We would take a sample from a population. So again, I'm going to use COVID-19 as an example. So let's say we get volunteers to test vaccines. We randomly assign members of that sample group to either a control group or a treatment group. Once that's done, we expose two groups identically, except that the control group receives a fake treatment, well, fake news, if you will. And then we compare the responses of the two groups. If the responses are the same, then we conclude that there is no evidence that the treatment variable causes a response. And that's all we can do. We have no evidence of causation. If, however, there is evidence of causation, that's all there is we have evidence of causation, and that's about all that we can state. However, that evidence of causation might be somewhat valuable. So let's consider this graphic here. This is a plot from the, I think it's MMWR. Yeah, MMWR, the Mortality and Morbidity Weekly Report. This is for Texas in the 2009-2010 flu season. It goes from April through September of a year and a half. So April of 2009 to September of 2010. And the bars represent influenza reported by the surveillance system laboratories in Texas. And so we see in April of 2009, there's non-zero influenza. And around August, September, when school starts, the influenza bars rise quite dramatically. And if you use the black line as a guidance, you could see from September through October, and it starts to decline at the end of October, November, going on through the winter season. So we have this big peak, if you will, in influenza, mostly type A. See, it doesn't have any H3N2, and there's actually a pretty good amount of H1N1. That stuff will kill you. That's the school season. So it begs some questions. Does going to school cause the flu? I would argue probably not, but I'm not a student anymore. If I was a student, yeah, it causes the flu. Best thing for me to do is stay home and play video games and watch TV, because then I won't get the flu. That's probably a reasonable argument, but not very good for your future. Does having the flu season around cause school attendance? What do you all think of that assertion? Well, I mean, clearly, flu does school's silent killer. There you go. That's about what I was looking for. Having the flu season does not make people go to school. People go to school, in your case, because you're college students, by choice. In regular school, you're mandated to go to school, and that's so that we can create a society of at least minimally trained people to operate our societal systems. Let's look at the next question. Does going to school contribute to the spread of flu? It would be hard to tell from just this data, because this data is just by a time of year. It hasn't segregated out whether they're school children or older than school children. But it's quite likely that from more segregated versions of this data, we could find a statistical relationship or an association that associates school attendance with increased influenza in a family. Does the spread of flu contribute to school attendance? Do people go to school to avoid flu at home? I would argue probably not. But again, we could ask that question of the data. And then are there any other variables that would have multiple impacts? So these other variables are called confounding factors, or I like this word, lurking variables. In wastewater engineering, you're dealing with solids, and there's three major kinds, the floaters, the sinkers, and then the scary ones are the lurkers. And if you ever saw animals, Caddyshack, you know what a lurking variable is. It's a Baby Ruth bar in the swimming pool. So examples of confounding variables with this influenza example would be cold weather, more time indoors, more close interaction, and a single data series like depicted in this diagram is insufficient. So we would need additional information. Now the surveillance laboratories that report to the MMWR, this is just one graphic. They have them supported by, they also have it separated by age cohort, so you could infer school ages, and they have institutionalized and non-institutionalized people, so you could separate out nursing home influenza. So you probably could get reasonable answers to the latter three bullet items. The first two I included because they're absurd. And when you're doing these kind of analyses, you need to think of that. Is absurdity inherent in the question? If so, how do I design my data science question to avoid absurdity? Okay, let's see how the Zoom chat's going. Oh, this is good. So now we're going to move on to our next topic. So that was simply an introduction to causality. If you see the word causality on a test, at least a test that Farang and I create, we're going to design a question that we're looking for the cause-effect relationship in causality. And if the question is such that you can't see an obvious, or not obvious, a discernible cause and effect, then we've created a question, probably intentionally, that does not show a causal relationship. And we'll study that more as the semester progresses. So our next topic is randomization. And if I'd been smart, I would have disabled a lot of this stuff and then rerun it live, but I'll just do it anyway. So to establish presumptive causality in data science experiments, we need some tool to help us randomize. And this is randomized in the sense that we can take our two groups, treatment group and control group, and separate them. So let's say we have 100 volunteers, and we want to put 50 volunteers in a treatment group and 50 volunteers in a control group. So that's easy. We need 50 signs that'll hang from their neck that have a T on them, and 50 signs that hang from their neck that have a C on them for treatment and control. The question is, how do we distribute those signs? Do you line everybody up in a line, one after the other, and then you hand the first person a T, the next one a C, the next one a T, the next one a C? Is that truly randomized? Let's suppose we lined them up by alphabetical order, which is a reasonable approach. We may not be able to argue that that is a randomized sample, especially if we have a bunch of people with names in the S's, like the Smiths. They could actually be species-wise somehow genetically similar compared to people that don't have the Smith last name, something like that. So what we want to do is we would like to, literally we could take a coin, and as each volunteer approaches us, we flip up a coin, heads your treatment, tails your control, and do that, and that would be arguably a type of randomization. So that's what is meant by randomization tools. So Python has quite a few built in, and just as an aside here, if you're using a computer to do random you're not really doing random. You're doing something called pseudorandom. And what pseudorandom means is we have algorithms that are indistinguishable from true randomness, yet they're entirely deterministic. If you happen to possess the starting seed of the random number generator for that computer in your back pocket, and it's very small because it's just a little bitty zeros and ones, electrons. If you possess the starting seed, and then a week later go back to the same computer, run the random number generator using that same seed, you'll get identical results. The usual starting seed that most of them use is the system time, some algorithm based on the system time, because that's always changing. But it's possible, if you have the seed, to replicate the behavior at some point in the future. So that's why it's called pseudo-random. For all practical purposes, it's random. The gambling industry with video poker has been using pseudo-random for a long, long time. And I'm sure they've been sued repeatedly. And all those lawsuits end in no finding against the casinos, because usually the plaintiffs end up buried in the middle of the Nevada desert somewhere. So you can see the bad movies I watch. It's random enough for practical purposes. In NumPy, there is a tool called random choice, a method called random choice. And what it will do is it will randomly select from an array elements of that array as needed. So for example, here we'll import NumPy, and we're going to create an array, a NumPy array called toGroups, that's the name of the array, and it's going to have two elements, an element, the string treatment, and an element, the string control. And then we will use the random choice method to choose from two groups, either treatment or control at random. So I'm just going to run this, and I have some notes here that says this also works directly on a list, so you don't necessarily have to use the array builder. So we get that, we get the word treatment back. Now we can instruct it, instead of just sampling from it once. Let's say we have those, I hate to do 100, that's going to be a long, well, let's go ahead and go for it. We have those 100 people, and we want to assign them either in treatment or control. We want to hang the sign around their neck, and we go ahead and hit it. And so you'll notice the slight change in syntax. I tell it what I want to select from, and I tell it how many times to do it. And so as the people are walking towards me, I have, first person gets the sign with a C over their neck, next person gets a T, next person gets a T, then a C, then a T, C, 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 T, C, and so on. You get the idea. So let me go back to the original single choice. And that is the random choosing tool. And so literally what random choice is doing internally is it's flipping an electronic coin, and if it comes up heads, it assigns you to one element, and comes up tails to assign you to another element. Now, if there are more than two things in the array, it reaches into its wallet and gets more than two coins. It can reach in and get a 6-sided die, or a 3-sided die, or a 7-sided die. The actual arithmetic of the random choice is not all that elaborate, but rather than showing it, we just use the tool as provided. So the difference of this function from all the others we've learned is that it will not produce the same result every time, although I wonder if there is actually a seed variable. We have time, let's go take a quick look, because I'm curious. See if it has a seed. Oh, it does have, let's see. Nope. So what I'm doing here is I'm using my friend Google, and I'm searching on some keywords, and I'm actually really want to get past all the ads and get some syntax. Quick, Jesus, halfway down the thing before we get the so replacement. Does not appear to have seed as an input option. So the seed is done somewhere else. But if we had the seed, we could make it roll the die the same way every time. That would be a damn handy tool to have in Las Vegas. Import NumPy. No, it doesn't have the seed. Let's actually get back to class. So it won't give the same result every time. So I'm going to run this once, and I get the word control back. I run it again, I get control back. I run it again, I get control back. I run it again, I get treatment back. So I do not get the same result every time. We can use the function to roll dice by making, in my case, a die array, which has the string 1, 2, 3, 4, 5, and 6 in it. And we will choose from that string one of the 6 options. And so think of that as we're rolling a die. So I go ahead and I roll the die. First time I roll it, I get a 1 back. Let me roll it again, I get a 5. Roll it again, I get a 2. You add the 5 and 2, you get a 7. I crapped out. Roll it again, you get a 6. So you get the point. Now let's suppose we want to simulate 6 rolls. So it's easy enough to use the roll my die as a single roll and repeat it 6 times. And so here it's done repeated 6 times. And in the context of what we've taught you so far, this is actually stupid programming, because why would you cut and paste the same thing 6 times? You would put it in an iterative structure. But here we'll do it 6 times. So I rolled it once, I got a 4. Second time I got a 4. Third time I got a 4. Everybody's betting on the roulette table for me now. Rolled a 5, rolled a 6, rolled a 1. Well, what happened on the 6th roll? The other die came up 6. So 6 and 1 is 7. Crapped out. So Braden, that's an excellent question. The answer is hidden away in Google somewhere. Random choice return index, I guess, would be the key to do it. Or you could actually roll on a dictionary, and that would give you your keys back, and you could do it that way. The other way to roll the dice 6 times is to use the random choice function, tell it what to sample from, and tell it how many times to do it. And it will have the equivalent behavior as these 6 lines of code. And if we do that, we get 3, 6, 5, 4, and 6 in the object called my dice rolls. My dice rolls should be an array, so the third position, 0, 1, 2, 3, I should get a 5 back. I've got a 6. 0, 1, 2, 3, because it's a random number generator. So you can interrogate elements of the object in that fashion. Now sometimes you want to do this over and over again a lot. And so as an example, let's create a game. So we've gone to the casino, and we've got Mr. Banks' attention, and he's going to let us introduce this new electronic game. And in this game, you roll 1 dice. And if it comes up a 1 or a 2, you lose $1. If it comes up a 3 or a 4, that's a push. You don't win and you don't lose. If it comes up a 5 or a 6, you're a winner and we pay you $1. And so in a gambling game, there's 2 steps that happen. First is you place a bet, then you make the roll. And so let's convert this game into a computer script. So we're going to start with a wallet, and in this case we'll just start with $1, and we'll have something called the place a bet function. And into the place a bet function we hand it the wallet, and it looks in the wallet, and if there's no money in the wallet, it tells you to get out of the casino. If there is money in the wallet, it takes $1 away and returns the wallet to you. Then we go ahead and roll the die, and the wallet's on the table, and what it will do is if the die comes up 2 or less, it returns the wallet as is, because remember we've already deducted the $1 when we placed the bet. If it comes up 4, we add $1 to the wallet. If it comes up less than 6, we add $2 to the wallet. The reason we're adding $1 right here is that that's a draw, and so you get your bet back. So we have to give the bet back, and here we give the bet back plus the win. And now we have a game. So the single play of the game would be look in the wallet, make a bet, make a roll, look in the wallet. So let's go ahead and play this fascinating game that's going to make the casino a fortune. So we started with $1 in the wallet, we placed the bet, we rolled the die, and we won $1. Now we have $2. Yay us. Let's play again. Except it starts at 1 every time. This time we started with $1, placed the bet, rolled the die, lost $1. Bummer. We have $0 left. So our next thing is let's do this over and over again a few times. So I want to play the game 10 times. I'm going to start with $10 and I want to see how I end up at the end. So ideally, if I'm really lucky and I roll the die 10 times and I win every time, I should have more than $10 at the end. If I'm unlucky and I lose every time, I should get driven down to 0 and they kick me out of the casino. So all I've done now is I've put the gaming part inside a loop, and I'm also having it print out at the end of each game within the loop how much is in my wallet. And you'll see another cool trick here. I've created a character called red to begin and end a red character, and you will see it print out in a different color. So I just ran this script. How many throws was 10? Actually, let's go back to 1. We'll do how many throws is equal to 1. And so I had $10. I placed my bet. I rolled the die. I got a draw, so I got my bet back. And after one play, I have $10 in my wallet. Let's play 2 games in a row. So I change how many throws to 2. Ooh, I got a draw the first time, and I won a second time. I now have $11 in my wallet after 2 plays. Looking good. Let's play 3 times. And I got 3 draws in a row, which would think unusual, but it can happen. That's the way statistics is. Now I'm on a losing streak. This is what the casino wants. I started with 10, had $9, $9 again, lost again, down to 8, $8 in a draw, and if we went on long enough, see, there's 1/3 chance of winning. Actually, there's 2/3 chances of not losing. So I think in the long run we would gain. Let's try 23 plays. And after 23 plays, I'm literally back to where I started from. But with everybody, you can. That's 23 plays of entertainment. I'm going to put this back to a 1 just to save space. And now let's suppose we wanted to really test that game. So we watched other people play the game and think, yeah, let me see how much money I have to start with to guarantee that I come out ahead at the end. So essentially what I want to do is simulate the behavior of either myself visiting the casino many times or a bunch of gamblers playing the same game. So I'm going to use the exact same code, except I make some function redefinitions. I want to suppress all the printing output, because when I'm doing a simulation, I may not care to have all the annotations that are going on. So all I did is commented out that print statement, that print statement, that print statement, that print statement. It's still the same game. I even left the printing tricks in that I'm not going to use. And we're now going to send in 100 gamblers. And each gambler is going to get $1 and up to 30 attempts to roll the dice. So 30 attempts starting with $1, chances of losing should be pretty high. And once the wallet goes to 0, it doesn't allow you to play anymore. We're going to take the results of my wallet for each game, store it in a variable called outcomes that happens to be a NumPy array. And then I'm going to plot the array as a type of graph called a histogram. And I have some other stuff here. I'm going to put another function on it just to help the eyes. And then I'm going to convert our outcomes array into a data frame so I can use the describe method directly. So I'm intentionally trying to keep that graphic at the bottom hidden from you. So you'll have to read this in more detail on your own to get the gist of it, but let me go ahead and refine that. We create a NumPy array called outcomes. That's where we're going to store the results of our gamblers. This is the same as before, so that's the actual sub functions to play the game. We want to play it 100 times for each play. So for each j in range to how many, we're going to start with $1. We're going to throw up to 30 times, and we're going to keep track of what's in the wallet. When the wallet goes to 0, it stays at 0. Then we're going to append that result to the outcome and do it again. So currently we're going to do 100 simulations and run it. And the blue bars represent the 100 outcomes. Let me make a quick change here. We're going to lose the red curve when I rerun this, but there's a reason for doing that. So that's the histogram. So we had 6 gamblers came out with $0. 12 gamblers came out with $1. 17 gamblers come out with 2. 16 gamblers come out with 3. Looks like 7 of them come out with 4, and so on. So this histogram is, if you will, a sample distribution of gambling success for 100 gamblers. And there's a lot of holes in it, and it's like, well, that doesn't make sense. Let's send 1,000 people in. The casino will never know. We do it again, and with 1,000 people, kind of the same kind of results. We have sort of a peak here around around $2. So that's what most of 200 of the 1,000 gamblers come out with $2. Quite a few come out with more than $2, and only a few totally lose. And then we will go to 10,000 gamblers. Hopefully I'll get some infill with this one. And so here it is with 10,000 gamblers. We have nice infill. And if we look at the mean value, so the average return starting with $1, throwing the dice 30 times is $4, with a standard deviation of 2. The minimum is a 0. The most anyone came out with was $19. The upper quartile is $6, so this is not a very good game for you unless the goal is to spend time. Now I'm going to turn this word density to true, and I'm going to plot a data model. The data model I'm going to use is something called a gamma distribution. We'll study that later on in class. So for the time being, it's just a model of the data. It has a parameter called A, and it has a location and a scale parameter, and you don't need to know what those are. Those are just knobs on a radio dial. So we adjust those knobs, and we're going to see how this behavior compares to a gamma distribution model of the data. And the red curve is my data model. The blue bar columns are the result of the simulation of sending the 10,000 gamblers in. And you might conclude that they're not perfect, but the red curve seems to be a pretty good descriptor of gambling performance for this particular game. And I'm kind of leading to the future because that's really what the statistical approach is to data science, is we want to find functional relationships like that red curve that describe our simulation behavior, and we use those functional relationships to extrapolate behavior of the future. But just if we don't trust it, let's go do 100,000 simulations. Now we got the law of a lot of numbers in our favor. And I don't know if this is going to crash my server, but we'll find out. At some point I can pick a number big enough that it just hangs. I may have hit that, so I'm looking at the word busy. Yeah, Rame, blame the class on me. I suggest if you go casino gambling, use cash. Don't use credit cards. And we will... Cool. So there is 100,000 gamblers that we grub staked. We took $100,000 and gave it to 100,000 people, and they went in the casino until the casino got tired of them. The median take was $4, so a casino wouldn't last long paying out that kind of money. The maximum take was up in the 19s, and in a few cases the casino won. So now we're working for the casino. How are we for time? We still got a few minutes left. Let's say for a casino, if we sneak in a single change. So when you draw, you don't get anything back. So losing and drawing are now the same. Now we only have a 1 in 3 chance of winning. Let's see what that does to the output. And what you just saw me do is what every casino on the planet would love to do. Be able to change a single character in the online simulation program, very deep in the program so you wouldn't get detected, and let it run again. And we'll see what we come up with. Keep in mind the red curve, when it does plot it, is going to be on the old data model. So we can think of the red curve as what things used to be before the casino made the change. And lo and behold, our casino is now looking better because the max payout's gone from 19 to 14. The median is $1, so the player comes in and leaves with the same dollar that they started with. We still get quite a bit of zero, and actually a lot in the zero. Now this casino is starting to make some money. We go ahead and return the game back to the correct structure. Save it. I'm not going to rerun that. So I hope you got the idea of the plotting and the red curve. Now at this point, you're not supposed to have any idea where I pulled that red curve from. Just think I pulled it out of my datum. But we will study that in the future. So what we've just done is a process called simulation. And that's the process of using the computer to mimic a real experiment or process. And in most cases in this class, those experiments will involve chance. And I'm taking this from the simulation chapter of inferential thinking. You'll notice that this is identical to what's in my notebook. This is also in our Data 8 sheet. It says we don't want to decide what we're going to simulate. When we build a script to do a single game, and then we build a script called a wrapper, if you will, that does multiple games, and then we put it all together in code. Press the go for it button, and before you know it, we have simulation. So we're going to do this first example. I got to get on the stick here, called the Monty Hall problem, and it comes down to a simple question: should I change my choice? So this is based on the Monty Hall example from a YouTube video. That particular YouTube video is a Khan Academy video of this exact example. It doesn't end with a statement, but we already have a small car. I found you another video. If you want to understand the significance of that assertion right there, you want to watch this video. This video is not at all scientific or engineering. It's comedy. Actually quite rude and filthy language comedy. So like all comedy. But let's consider this particular game. So the gist of the game is that Monty Hall, who was a television game host in my youth, trying to remember if it was, I think it was called Dialing for Dollars. No, that was a different show. I can't remember what the show is anymore. But at the near the end of the game, a contestant is presented with 3 doors: door number 1, door number 2, and door number 3. And then the actress was called Carol Merrill, who would stand in front of the door and open it. Kind of like predates Vanna White, same general concept. And the contestant is told that behind one of the doors is a wonderful prize. And in our case, it's going to be an automobile. And behind 2 of the doors is a chump prize, in this case, goats. So the contestant is allowed to pick a door. And once the contestant has chosen a particular door, the game show host goes to one of the non-chosen doors and opens it. And they always reveal a chump prize in the non-chosen door. And then the contestant is offered the chance, do you want to change your guess? So for example, let's say contestant picked door number 1. So 2 and 3 were not selected. And the game show host opens door number 3 and it shows a goat. And then the contestant is given the opportunity, do you want to change your guess from door number 1 to door number 2 or not? And using classical probability theory, it's pretty straightforward to show that probabilistically your chances improve if you change your guess. What all these have, the one weakness is, in real life you only get to play the game once. So that's the Monty Hall problem. Should the contestant stick with the initial choice or switch to the other door? So using classical probability theory, it's fairly straightforward to show the chance that the cars behind the original door is 1 in 3. After the goat is revealed, the chances that it's behind the non-chosen door is 2 in 3. And so if you switch the decision, you increase your probability of getting the car. And if we have harder situations, we can use this same construct to simulate and ask complex questions. And you're going to have an example of that in Let's Make a Deal was indeed the name of the TV show. Thanks, Frank. You will indeed have a chance to play with this in the lab. So here I have some script to set it up, first we have a function that returns the other goat. So if we enter the function with goat number 1, it returns goat number 2. If we enter with goat number 2, it returns goat 1. Then we create an array of doors, and the doors have a car, goat 1, and goat 2. And we can create an array called goats, goat 1 and goat 2. So we have these two arrays for all the objects and then the chump prizes. Then we're going to create a function called the Monty Hall game, and the user is going to guess at random from doors, a user guess. If the guess is goat 1, then we return the guess goat 2 and car. If the guess is goat 2, we return the guess goat 1 and car. If the user guesses the car, then we reveal one of the other two doors, and then return the guess and then the revealed doors. So the first thing we do after building the function, and this is classical programming that you all need to do, is you want to make sure the function's doing what it's supposed to do. So we're going to have I march through the array and print out the contents. So A is going to be an object that's the result of the Monty Hall game. You'll notice that the Monty Hall game has no input. So we run that, and sure enough, the contents of the array are goat 1, goat 2, and car. The 0 element is goat 1, the first element is goat 2, and the second element is the car. Now we're going to go ahead and keep track of how many games. Let's just do 10. So we create some empty lists to store the user guess, the revealed, and the remaining contents for each game. So we will simulate the game how many games, and so we run the game once, and then when we get out of the game, we get whatever the user guessed, whatever was revealed, and whatever was remaining. And then we'll create a data frame from that output and look at the contents of that data frame. There we go. So our 10 results, the user was lucky and guessed a car the first time. They were revealed goat 1, and then the unrevealed one is, they revealed goat 2, unrevealed is goat 1, and so on. And now we'll get the count of each item in the first and third column, and we'll plot everything. And this is based on 10 plays. So in 10 plays, if your original guess turned out to be the car, 2 of the 10 people got the car on the original guess. 6 of 10 people guessed a goat the first time, and 2 of 10 people guessed goat number 2. If they changed their guess, 8 of 10 would have received the car, 2 of 10 would have received a goat, and there were no remaining guesses in goat number 2. So let's up the count. Let's go from 10 games to like 10,000. So we want to see if this yellow-purple relationship holds, because that would be a good strategy for here we go. Run the game, create the frame, get the amount. That would be a good strategy for playing such a game. So in 10,000 trials, changing the guess produced 7,000 cars, 2,000 goat 1s, and 2,000 goats 2s. So to interpret the results, according to the plot, it's a superior strategy for the players to switch doors after the game show host has revealed a chump door. So I'm going to leave you with this question before we move on to the lab. Does changing doors have a causal effect on the outcome? So anybody speculate, can think about that? What do you think? It's a tricky question. Okay, so Braden says, yes, it has a causal effect on outcome. Andrew says no. Perfect, that's what I was looking for. I think I would tend to go ahead and, if you look at the way the language is asking, maybe. Good job, Ryan. Yes, no, maybe. I don't think so. Life isn't fair. So Malcolm's in the middle. So does changing doors have a causal effect on outcome? So think of the words that were asked there. If you change the door, your outcome is 7,000 cars. So I would say yes, there is a causal effect on outcome. The deeper question is, does changing doors have a causal effect on probability? And that would be no. The probabilities are predetermined by the nature of the game itself. So when we're talking about causality, we need to be quite precise in the language that we use. If I don't change door after making the first guess, the probability of the remaining door still having 2/3 is completely unchanged by me not changing. The probability is defined by the game. But changing doors as a strategy has an effect on my outcome. I have a greater chance of driving away in a car rather than riding off the set in a goat. So I will leave that with you, and probably the most confusing lecture so far, but we got more coming. And I will prepare this for handing off to Farang for the laboratory. So thank you for your attention and participation. And let me quickly look here. I think we hit all the items of this. Yep, we got the confounding factor, randomness, rolling dice. There's the Monty Hall problem. So I would say we covered that, and let me stop sharing.
If you want to go on a break, go on a break. We'll start at 9:35. And if you have any questions about your notebooks and your previous lab assignments, I will be sitting here ready to answer.
Okay, you should be able to share your screen now, Farang.
Thank you. I'm doing fine, Braden. Thank you for asking. How are you doing?